So, good afternoon. Welcome to Krishna's classroom. Now, we begin with the building up of the proof of the Riesz representation theorem. I have once again put the statement of the theorem on the board. We will just recall it to be at home with what is happening. Let X be a locally compact Hausdorff space and lambda is a positive. So, X locally compact Hausdorff space. Lambda is a linear functional on the vector space CCX. We are assuming this to be complex valued functions defined on X. Then it's a vector space over C. Then what it says, so lambda is from CCX to C and lambda is positive. Which means whenever F is non-negative, lambda F is non-negative. That's the meaning of that. It's a positive linear function. So this is the given data, and then the conclusions are there exists a sigma algebra M, a measure mu on X, so that X M mu is a measure space and what you have is this lambda F can be written as integral over X F. So you can express the positive linear functional or the positive linear functional induces on X a measure such that the action of lambda on F can be expressed in the form of an integral, namely integral over X ft. This is the content of the theorem. Okay, and then of course it follows from there that it's a unique positive measure mu on M, and then so the uniqueness has to be proved. So we have to prove the existence of such a measure. So our problem is to prove the existence of such a measure, and we prove that it is unique. So there is a unique measure. So to prove that, though before that we have to set what exactly is our sigma algebra. So on X we have to find out a sigma algebra and then a positive set function from the sigma algebra, okay, so that such that it defines a measure. That means all the conditions required of a measure are satisfied on the sigma algebra. Okay, so that is something to be proved. So that would take care of the existence part, and then you have to also prove that this is a unique measure that is determined in this way. Okay, but what are the properties that it has got? See, one can prove that the measure of every compact set is finite. The second property that we have to prove is that for E belonging to the sigma algebra, the measure of E is infimum of mu of E, where mu of V, where E is contained in E and V is open. So you approximate from outside the element of the sigma algebra by open sets. And for each open set, you have mu defined and then take the infimum of that. And before that, a lot of things are to be proved, like this, the monotone property of mu, etc. Okay. The other property is that for every E belonging to M, the following property is satisfied. Mu E or E can be approximated from inside by compact sets. In which cases? For all open sets E, and also for all sets in E whose measure is finite. Okay? And in that case, you see, you are approximating from inside. For E, you have the measure defined, and then take the supremum of all these measures over the collection of compact sets which lie inside E. Okay? So that gives you the measure of K. Finally, one can prove that this is a complete measure. So these are the things that we have to prove. So we first take up the uniqueness and then we work on the existence. Okay? Strictly speaking, one should first prove that it exists and has all these properties. Okay? And then one can prove that it is unique. But we just first work out, because it involves a few steps, assuming that we have successfully constructed the measure and all these properties have been established. We can show that the uniqueness of the measure that we have constructed. So our first task is prove the uniqueness. Okay. Now, one remark which I have made last time itself is that, you see, this lambda is not a real linear function, and it is working on all complex valued functions. And you get complex value. You in fact get complex values. So it's a map from, as I have said, it's a map from CCX to C, but with the property that lambda is positive. Lambda is positive means whenever lambda f is such that lambda f is greater than or equal to 0, then f is okay. Lambda f is non-negative whenever f is positive. Okay, that's the positivity, because you will see that when we define the measure, because the measure that we define has to be a non-negative number, and you see that in the definition this will be. Okay. So the positivity is something that is assumed straight away. Then for such uh, linear functionals, we have a sigma algebra determined on X and a measure determined on X such that this representation theorem is valid. Anyway, this is called a representation theorem. The lambda is represented by this. Okay, I mean we have seen the other side of it. That is, if mu is a measure, or x is a, with x of course locally compact, this is a measure space. Then for every f belonging to CCX, we have integral over x f d mu is well defined, and as a linear function on CCX, as a linear function on CCX, which is non-negative or which is positive for every f greater than x. So the converse is something which is already there. And the question that we are asking at this stage is, or in this theorem, what we are trying to resolve is this. Suppose a linear functional lambda on CCX is given, satisfying the properties that lambda is positive, is a positive linear functional. Then we prove that there exists a sigma algebra M and a mu such that the lambda f is expressed as integral over x f t. Okay, right? So we are actually proving the converse of this result. The converse of this result is, in fact, the whole build-up that we made was to give a meaning for this integral. That we have done. Now we are actually going through some of the consequences. And we see that if f is a non-negative function in CCX, then, or it's a positive function in CCX, then what we get is that if you define lambda f defined as integral over x f d mu determines a positive linear function This is the result that follows from this particular disposition. But what comes out, what we try to prove in our theorem is that given a positive linear functional, can you get back your measure space, okay, with the identification that lambda f is written as the form. And this is a central theme of this particular theorem, and which we. Now I think with these remarks we shall start proving this. So we shall assume uniqueness. First, because it's simple and we dispose it off. So this theorem is essentially an existence and uniqueness theorem. Okay, so there are two parts for it. First, proving the existence of such a measure space. Secondly, with the desired the properties that are listed out, then you are actually verifying the properties of such a measure space, and then we prove that the uniqueness of this measure. That's our task now. So we assume the measure space has been constructed giving the such that all the statements of the theorem hold. But we shall come to that. So far we have not done it. We will do it. Okay. Then we prove that mu is uniquely determined. And you know that mu is essentially as a map from script m to r. In fact, r plus union 0. It's a non-negative function defined on the sigma algebra. Okay. Now claim. Okay, what is the meaning of this? This means for every E belonging to the collection M, mu of E belongs to 0. It's a real number, it's a non-negative real number. So we show that, so to show that mu is unique, we proceed as follows. Assume there are, okay, first of all, we make an observation. What is observation? See, you are taking E belonging to M. Now, there are two properties which we already have established. Or we assume that we have already established. These are given in the statements of the theorem. For K, you have mu of K is finite. This is one property. Then this is designated as 2, I think. Yes, and 3 as mu of E equal to infimum of mu of V open in X and V contains E is contained in, or I will put it this way, E is contained in V open. This is something that we have. And the fourth property is this, as I said in the beginning, can approximate these sets from within using compact sets. So there are two statements there. One, of course, what we say is that mu E belonging to script M is equal to infimum of mu K for K, a compact set contained in E compact. And this is true for every E open. That is one statement, one part of this statement. And the second part of this statement is this. The second part of the statement is mu E equal to infimum of k mu k contained in V See, the first statement is valid for E open. The second statement is for every K belonging to, every E belonging to N. And mu E is 5. There are two statements here. The first part of the statement is only for open sets. So for all, it is valid for all open sets. And this is valid for all E belonging to such that mu E is finite. Okay, now we use these properties together to come to the conclusion that it is sufficient to prove the uniqueness on compact subsets of X. How do we conclude that? Look at this. So whenever E is open and it has finite measure, okay, whenever E is open, then mu E is given by this one. Okay. For any element of M, not necessarily open, but with finite measure, you see that mu E is given by the same state. So these are the two things that we have. So what do? We start with an open set, okay, and you see that if E happens to be open, then you see that this statement is valid, okay, right? Therefore, for every V open, this is true. So for every V, the set of all this is valid. For every V open, for every V open in X, this statement is valid. Okay. Now go to the previous statement. What does the previous statement say? Okay. Mu E for every E this is supremum. Now here it is infimum of E containing. Now this is satisfied. Therefore, you see that eventually all that you need prove is that for every compact set, so through compact sets you can get to open sets, and through open sets you can define the measure on every what you call subset of X. Okay, I mean this is not a measure. This will turn out to be what is called an outer measure. So it is, so uniqueness would follow if it is shown that if mu1 and mu2 are two measures, mu1 so we have reduced the problem in this stage to proving uniqueness on all compact sets. Okay. So that's our next task. So let us prove that. So this is the see, we have something that we would have already proved is that mu of k when k is compact, k belongs to M and mu of k is compact. This we would have already. Okay, now we shall use all these things together to prove the uniqueness. Let me see how do we work this out. Assume lambda determines two measures, two mu1 and mu1 and that means lambda f which is also equal to integral over x. Yeah. Okay. So we sufficient to prove that, to verify that mu1 k so that is our task. So let us work on this. Now for that we make the following observation. Fix k. Let epsilon positive be to 1. Then the properties 3 and 4 implies there exists a V, an open set V containing K such that mu2 of V is less than mu1 of or mu2 of K plus. What does this mean? How do you get that? This is because of the form. We have K given, now you have V, okay, and you have K is a compact subset of, and on both V and K, mu is defined, okay, and then what you have, we are having the result that mu K is defined as, or turns out to be, we have written it, mu2K turns out to be what you call infimum of mu2V E open. This is what you have. What does this mean? Because of this relationship, you see that, mu2V is essentially mu2 of K from this, okay. Now it says that you can, given epsilon positive, you can choose a V which lies arbitrarily close to K. Okay, it's only K plus a very small region to make it open. Okay, that is expressed by, in that case, you see that from this relation, you see that mu2K or mu2V is less than that means within this epsilon, okay, you can find a V such that mu2V is less than mu2K plus. This is the result that you obtain. So, what is the position? K is compact, V is open. Okay, so we have immediately Urysohn's lemma. By Urysohn's lemma, there exists a F, that means a continuous function which compact support on X such that K is subordinate to F, which is subordinate to V. What does it mean? It shows that, or it says that, you see, on K, the function F is 1. On V, or the support of F is contained. Okay, so that is on k on and support of now these are the implications that you have. This is what you can draw from Urysohn's lemma. Okay, so the support of f is somewhere here. So you take such a specific function. So we shall work on this. Now you see that let us compute mu1k. What is mu1k? Mu1k is essentially the integral over x, the characteristic function of k dmu1. That means you are picking that the measure of k. Okay, right. Now this is not CCX. It's not necessarily CCX. All it says is it is so. Right. And this you know is less than or equal to integral over x, the f that we have taken, f dv. Okay, right. And this is from the property of the integral. You take the characteristic function and integrate over x, you get the measure of k. And this you know that the f that we have constructed here is having the property that chi k is less than or equal to. So we are using this. This is from this one. Okay. And this, of course, by definition, this is lambda. And this, you know, is again equal to, if mu2 is another measure determined by lambda, this is equal to integral over x f d mu2. And this, you know, we have already seen that this is less than or equal to integral over x chi v d mu2. Okay, and chi v f is less than or equal to chi v. Therefore, what you have is this is equal to mu2v, and what is that we have? mu2v is less than mu2k plus. So what have we proved? We have proved that mu1k is less than mu2k plus x. Okay. Now, you know, and this implies mu1k, this is true for every epsilon positive, is less than or equal to mu2k. Similarly, by interchanging mu1 and mu2, we get by the same argument, mu 2k is less than or equal to mu 1. So together, we obtain mu 2k is for every k, and consequently with the other properties as I have explained earlier. That is, mu is uniquely ft. This is what we prove. So we have completed the proof of the uniqueness. Now, having done this, we take up the major part of the proof, namely proving the existence of the measure space. Of the measure space x mu such that so that would complete the proof, but this part is rather lengthy and we have to prove it through several steps. So one after another, we'll take it up and prove it, starting from the definition of mu. Okay, so that's our first task. So there are two things to be done, namely, we have to identify m, and on that, we have to identify the set function. Okay, we show that lambda actually determines such a what you call a class of measurable sets, and on that a measure mu, and giving the property that lambda f is equal to integral over f d mu for every f belonging to CC. So with this, let me wind up today, and let me start from tomorrow on the proof of the theorem, going through all these steps. Our task is rather lengthy, because we have to first identify what is going to be your m, and then define mu. On that, we shall need all the results that we have established in the past. Work this out. Thank you very much.